Ma'am, live streaming is on, ma'am.
Okay, sir. Hello. Hello.
Hello, sir.
Could you hear me, ma'am?
Yes, sir. Is that okay, sir? Mr. Padmanabhan, sir, just check whether your audio is audible. Sir, can you unmute and talk?
Hello. Good evening, ma'am. Is it audible?
Yes, a little more louder, sir.
Now is it audible, ma'am?
Yes, sir.
Okay.
Some background noise is there.
Noise. I think this is external noise that's coming. Is it like wind?
No, sir. Now it is okay, sir.
Okay. Okay.
Okay, sir. We'll be going on live now.
Okay.
I'm starting the recording, ma'am.
Okay, sir.
You're ready to go, ma'am.
Yes, sir. A very pleasant evening to one and all present here. Education is not learning of facts, but training of minds to think, by Albert Einstein. With this quote in this pleasant evening to refresh and create an impact onto the mind, Department of Electronics and Communication Engineering, Savita Engineering College brings to you a webinar on autonomous mobile robot navigation and overview by Dr. K. Padmanabhan Panchu, Assistant Professor, Department of Industrial Engineering, College of Engineering, Gindi, Anna University, Chennai. Now let me introduce about my college and the department. Savita Engineering College, established in the year 2001, an autonomous institution which follows the Finland-based education model, and we march towards less is more concept. Our college makes the students job ready by providing Industrial 4.0 curriculum which imparts the 21st century skills. Project-based learning integrated with subjects improves the student's skill set and makes our learners to be the best, which is the motto of our college. The Department of ECE was established in the year 2001. Our vision is to develop the department into a state of art with center of excellence in electronics and communication engineering education on par with global standards. The Department of ECE as well experienced faculty of proven ability and diverse specialization. The faculty actively involves themselves in research in the field of robotics, VLSI, MEMS, image processing, and embedded systems. Now I would request Dr. Padmanabhan Panju, sir, to take over the session. Please, sir.
Thank you. So
Sir, you can share your screen now.
I just went. Is my screen visible, madam?
Yes, sir.
Okay. So, good evening, one and all who are present here in this webinar. So first of all, I would like to thank the authorities of Savita Engineering College for giving me an opportunity to share my knowledge in this autonomous mobile robot navigation. So let me introduce myself with a small and 1 minute introduction. So I was basically a production engineer who has graduated out from GCG Coimbatore in 2004 batch, and later I joined Sri Ranganathan Industries as production engineer, and later I joined ME Industrial Engineering in Anna University, Chennai, and completed it in 2008. And after completing, I joined Avtech Limited, where I worked as an industrial engineer for 1 year. And later I joined Kongu Engineering College as assistant professor, and I worked there for just 3 months, and I joined in Anna. This is my short history. So I worked in various capacities as industrial engineer and production engineer also. And after joining Anna University in 2009, I started my both teaching and as well as a research career. I've taught subjects like robotics, manufacturing systems modeling, simulation, and reliability engineering. And my research area is about task allocations for multi-robot systems. So basically, I got inspired about this multi-robot systems from a seminar topic which we conducted in Congo Engineering College. So I thank Congo Engineering College for having given me an opportunity to attend that uh, uh, seminar where I got this idea from doing this research. So after that, I got interested in robotics. Basically, I don't have any idea about programming and other things till I complete my B. After my completion of B, I thought of when I came into the industrial engineering department, I have to learn programming. That was my main important thing. So many mechanical engineers will find it difficult to learn programming, but it's very interesting when we start learning. So that's how I came into robotics. When we talk about robotics, it's not, we cannot be a mechanical engineer alone, or we cannot be a computer science engineer alone, we cannot be a communication engineer alone, or something like that. We have to be a multidisciplinary person. So we have to know at least every part of it. So that is how it is. And you can verify my name and credits. So all my publications and what are things, if you type my name, you will know it. So it's all open today. We need not, just to give a short introduction, I've given you this. So now let us start with this autonomous mobile robot navigation. So is my next slide visible? Okay, the contents of this presentation, I've arranged it like this. I will give you in this 4 simple parts. So first we will, so there are mixed participants. We will see what is autonomous navigation first. Then we'll see about what is the need for this autonomous navigation. And I will explain you how these robots navigate in nutshell, not in deep. So I will just cover the boundaries, okay, and we'll see what are the challenges in autonomous navigation. So this will be helpful for many of the researchers who want to do work in future research and other things. So first we'll cover some basics. So for people who are newbies in this autonomous navigation, will understand what it is. So you can see that there is a picture here wherein there is a robot, industrial robot, which is placed in an environment. And you can see that the robot is sensing something. So when so if suppose if you want to plan something, if you want to move the robot from one point to another, so how to do it? We'll just say, for example, we have point A here and point B here. And if I want to move from point A to point B, we should know how to move. If you are manually moving, we can control the robot by manual controls, by moving right to left, whatever it is. Suppose we have some obstacles here and there, and the robot starts from here, and you can move, navigate the robot manually to reach the point from A to B. But what happens if we want to move the robot by itself? That is, without the intervention of human, if we want to make the robot move from point A to point B, so what should we do? Imagine a situation where you are being taken blindfolded. That is, your eyes are tied. You are being taken to a new place, left into a forest. What will be the situation? So this is the situation for a robot too. When the robot is kept in an environment that is unknown to it, the first thing the robot will try to do is it will sense the environment. So sensing of the surroundings. Once it senses the surroundings, it will come to know what are the obstacles or what are the free ways there where it can move, and that is called perceiving the environment. Sensing is different, perceiving is different. So sensing and perceiving, there are two different things. So when you sense something, say for example, the robot is not only to navigate from one place to another, it has to do some important or useful task. So suppose if an object is being sensed, so how it senses, whether it is senses as an object that it has as an obstacle, it may be an obstacle also, or it may be an object that it has to pick up. So how it has to identify. So that is called perceiving the working environment. And next it has to plan a trajectory and execute a proper path it has to run. So planning a trajectory means, so suppose if a map is supplied, there are many different situations. A robot may be given a map, may not be given a map. When a map is supplied from point A to point B, it has to plan a path. So that is called as planning of the trajectory. And avoiding obstacles. So you have to maneuver the obstacles. You should not hit the obstacles. Obstacles may be human beings also. You can see human being in loop. You can see other robots in loop. All this happens, and you have to move to the commanded position. So the commanded position point B is given. There you have to move, and intended speed, or you can say other characteristics. So whatever it is, sometimes you may carry an object the robot may carry an object which has to be kept without any vibrations or something. So the speed is also important. So it depends upon what object you carry. So, and even maneuvering through narrow spaces also. All this encompasses the autonomous navigation. That means autonomous navigation in nutshell is how we are going to make the robot move on itself, how it is going to sense the environment, how it's going to perceive the environment. By all these things are by itself. How it's going to plan the path, how it's going to avoid the obstacles, how it's going to move from point A to point B, and then what are the speed characteristics and other things. So this is called autonomous navigation. So let's move on to the next slide. So what is the need for this autonomous navigation? So when if you want to control only one robot, so one human being is enough, right? So when one human being is there, it's very easy. So nowadays, many students are participating in these robotic competitions. You could see that they used to control the single robot with their joysticks and remote controls. So when we are controlling and navigating this one robot, it's very easy. So, whereas there are situations in which nowadays you can see this picture. This picture I've given you the Amazon's warehouse. So in this Amazon warehouse, there are multiple robots in operations. So when there are multiple robots in operations, if a robot is not equipped with these autonomous capabilities, and it is very difficult for the factory engineers to control these robots. And you have to, every robot has to be manned by every man, and it does not serve the purpose. So only when this autonomous, the robot has the capabilities of making decision on its own, and given a task, it has to do it by itself. So that case, we need autonomous capabilities. So that is one warehouse. We can see nowadays in the COVID pandemic like situations. So many of the hospitals, they are just in starting stage. We are trying to use single robot to carry medicines and required facilities to the patients and keep people away from each other. So their hospitals are trying. We can see the daily news about that. And the material transport. So when the materials are very heavy, so how robots are used to transport. So we need autonomous robot navigation, search and rescue missions, and another. You can see another picture on how search and rescue. This is a fictitious picture, but not actual. So in future, it may be helpful in search and rescue missions and object transportation. So in material transport and object transport, I try to differentiate with so cooperative object transport, when two robots together try to carry an object, and even in space exploration. All these things for autonomous robot navigation is much required. So having said this, how this autonomous robot navigation varies with the situations, variations in the autonomous robot navigation. We can see that The environment in which we are employing or deploying the robot may be of indoor or maybe of outdoor. The navigation capabilities differs for indoor and outdoor navigation. In indoor, the floor space will be of known floor space. In outdoor, an unknown floor space may be there, or sometimes even known floor space. But whereas in outdoor, we may use sensors like GPS and other things, but GPS, the accuracy of GPS is very less in indoor, and it is only plus or minus 3 meters. That is not um, good for indoor environments. So if you see the indoor environments, we have to use special sensors to find out the location of the robot, and the problem comes there. So, and even in outdoor, you can locate the robot with the help of GPS. So you can easily locate yourself in a map, in a Google map, in outdoor. Whereas if you go into a large factory, it will not, the GPS will not be much accurate. So you cannot navigate a robot using GPS in indoor. So even and if you consider the terrain, an indoor terrain will be easy for a robot to move from one place to another. Whereas outdoor terrain like this, if the robots are very difficult to move. So because the terrain is uneven, it may have ups and downs. All these things will be there in outdoor navigation. So similar way, structured and unstructured environment, we can call a structured environment is where a factory type of location, and unstructured environment for a search and rescue mission will go in an unstructured environment. In structured environment, a map can be available. So a factory floor space map can be available. You can give where the machines are placed and where the robot parts are there. Whereas in unstructured environment, it is very difficult to give the map. The robot has to create its own map for it. So that is the problem here. And static and dynamic environment. Static means if suppose if you employ or deploy only one robot in a situation, then the environment may not have anything and change with respect to the robot. Whereas in dynamic environments, and you may have people in loop, you may have other robots in loop. So the robot has to work and navigate within this environment. So, and based on robot characteristics, also the navigation capabilities required may be different. So you can see wheeled mobile robots. So wheeled mobile robots, they used to have odometry sensors and other things. You can see legged mobile robots. So wheeled mobile robots moving in an uneven terrain for wheeled mobile robot will be difficult, whereas they use legged mobile robots for moving in uneven terrain. And you can see flying robots, so which can move easily from one place to another if the space is free, and even underwater robots are there. So all these things will have different navigation. So the navigation means, so the first basic thing is how it senses, then how it perceives, how it moves. So here robot based characteristics in movement only they differ the navigation, and the various sensor capabilities are there. So you can see radar systems which can use to find out the objects, and even nowadays for lidar are used to take the 3D map of the image. So in simultaneous localization mapping, so I'll talk about it a little bit later. They use lidar systems and GPS outdoor systems. They can use GPS laser systems for finding out the distance of objects. And sorry, there is some mistake here. And IMUs, inertial measuring units. So mainly this type of walking robots and flying robots will use this inertial measuring units to find out this rock pitch and yaw movements, and the location of the robot in a space, and even motion sensors like so there are to find out the motion, the wheels and other things. So these are some variations in robot navigation. So now let us look into some terminology for those people who are new to robotics or new to this area. Need to understand certain things in this. So I've given a list or a gist of terminologies that I will be using The first one is about state estimation. State estimation means, say for example, if suppose we have a robot, and if this robot is, say, we have a environment like this, and if we have a robot here, and it is pointing towards this direction. And state estimation is nothing but we are estimating the actual location of the robot with respect to x and y, and also theta. So there are three things: the coordinate x, y, and the heading theta is important. So this is called the state of the robot. So suppose if this is 2 and this is 3, so 2 comma 3 comma 45 will be the state of this robot now. So it is defined as estimation of pose. We call it as pose of the robot with respect to the environment from time to time. So at time t, it may be in this position. After time t plus 1, it may, based upon the controls given, say if I say move forward 1 meter, it will come here. So it will come here and it will be posing out in this direction. So that is how the, with respect to the time, how this pose changes. And next comes localization. So given a map, instead, so as I said, I have given you an example of imagine yourself being left blindfolded in a forest. So that is the way the robot also will think. So when it is kept in an environment without a map, or even if you give a map, it has to find out where it is in the map. So how that robot localizes itself on the map. I've given a map to the robot, and the robot has to know where it is placed on the map. If initially I supply the data, you are here, then it may know that it is localized there. And mapping, sometimes in search and rescue operations, you may not have the map with you, so you have to create the map. And estimating this pose with the map is called as mapping procedure. So that means the robot itself is going to create the map for itself. And sometimes we will not have both this information. Localization information also will not be there. Mapping information will also not be there. So it has to create a map and localize itself on it. That is called as SLAM problem. It's a problem that is nothing but simultaneous localization and mapping problem. So, sorry. And after this, once you have created a map, and you are available with full map and all obstacles wherever it is placed and everything, and if you want to move from one place to another, you need to have a plan of how you are going to move from one place to another. That is called a path planning procedure. So certainly in many situations there are two different types of path planning is possible. One is online path planning, and another one is offline path planning. So when full map is available, you can go for offline path planning. So initially, before you start from point A to point B, you know how you will move from point A to point B. Whereas in online, you may not know how to move. So you will be start moving, and while moving, you will plan for the next steps. So that is how, that is otherwise called as movement algorithm. So finally, once you have planned the path, then you will go for navigation. Navigation is nothing but act of controlling the robot speeds and other things, and maneuvering with obstacles and finding out. So even if you have a planned path, sometimes an obstacle may come in between. So you have to take decisions there, whether to stop or whether to take a different path or whatever it is. So the such procedure of controlling is called as navigation. So now let me discuss about this mapping problem and localization problem, and we'll move on to. I've arranged it like this. First, we will discuss something about this simultaneous localization and mapping problem. Then we will go to path planning, and once these two things are done, next is about just control through the path. So that is about controlling. All these three sections we'll see. So mapping, it's a problem of integrating the information gathered with the robot sensors. Say for example, when a robot is kept it in an environment, it will use its sensor, and sensors may be like, as we have eyes, the robot may have a lidar. So it may use a laser to view the objects, or it may use a camera to view the objects. So based on the camera image or based on the lidar image, so it may take the image and perceive it. So once it has sensed, it will perceive it, and it will think about what the world look like. After taking senses, it will put that senses. Suppose if it sees a wall, and that wall has to be represented as an obstacle in the map. So that is how the representation is made in this environment, and this has to be changed from time to time. When the robot moves from one point to another, this map has to be keep on updated. So when you face a wall, it has to represent a wall. Then if it takes a left turn or right turn, accordingly that map has to be built. So that is how this mapping is being done. And localization is, once the map is there, how where the robot keeps itself on the map. So that is called as localization. That is estimating the force, where it is and in which direction it is pointing. That is called as localization problem. So if the localization is wrong, then the the robot's movement. If suppose if you have perceived that you are in actual robot position is in north direction, and if you perceive that the robot perceive that it is pointing towards south direction, the map that it builds will go wrong. So that is how this goes on. So now let us look about simultaneous localization and mapping. So this problem is like a chicken or egg problem. You could have heard this question many of times. So which comes first? Whether the chicken comes first or egg comes first? That is the question that most of us even would find it very difficult to answer. So that is the same problem for robots too. So whether the robot localizes itself on the map first or it creates a map first. So that is the problem. So the robot thinks where I am, where should I go, and how can I go? So it should create its own map and localize itself on the map. So without map, you cannot localize. Without localization, you cannot create a map. So that is the problem actually. So that is what we in this research area represent it as chicken or egg problem. So which one do we keep first? So it's nothing but it's a computational problem of constructing and updating a map of an unknown environment while simultaneously keeping track of an agent's location within it. So they will start with one point, and they'll start sensing the objects in it, and they'll start constructing the map and as well as localizing the map. So where this simultaneous localization mapping is applied. So it's applied in everywhere where indoor or outdoor. When an environment is new, it has to be done with this SLAM. And outdoor, you have to go for this SLAM definitely. And even in all the land, water, and space, you need this SLAM. And almost all applications, newly exploring applications, you need this SLAM. So we'll talk about the definition of SLAM. So it is nothing but what is given and what we want. So given is robot controls. Say for example, if it is imagine that we have an autonomous driving car, and this autonomous driving car, if suppose you press your accelerator, then it is called as you control sequence. So I pressed the acceleration for 1 minute, and I've gained an acceleration or something, or velocity, whatever, something that is called as controls. So whatever is given as an input to the robot or whatever it is. So this is called as acceleration. So 1 to t is from time 1 to time t. So it may change from time to time. Initially, I could have pressed, then I could have given a brake, then I could have again pressed the accelerator, something like that, whatever be the control. So there are continuous controls. So even for an autonomous robot, these are the controls that it has to take it as a decisions. So after giving the control, so for each and every control, it will make an observation in the sense, so what it senses from the environment. Say for example, there are several sensors in a robot, like it may have lidar, GPS, it may have motion sensors, IMU, whatever it is. So all these sensor readings are put it as so for control you given, what are my senses observations. So I have observed an image. Okay, I observed an object, whatever it is, that comes here. So for each observation, for each control, there will be an observation. And based on this, what I observed, that I will represent it as map M in the environment. So, and based on that, my location x of t can be identified. Say for example, initially there is a environment like this, and imagine that a robot is placed pointing towards this direction, and imagine that there is an obstacle here, and the robot is sensing in this direction. The robot is seeing everything in this field of view. This is the field of view for the robot, and when this is the field of view, and imagine that there is some algorithm running here inside this robot, and this algorithm, how it perceives this environment as, it can see only this. So you can see that this object, the object present here, objects the field of view, and it cannot see this rectangular corner here. The robot can only perceive an image like this. So it will see a line like this, it will see a line like this, and from here it will see a. So this is what the map for of as of now created by the robot. So when the robot moves from one place to another, say for example, the robot has moved from here, it goes like this, and it has turned like this, and now it is posing like this. So what the robot will perceive now? So now if the field of view is same like this, now the robot can perceive and another corner here. While moving, if it could have continuously scanned everything from here, so it could have taken all this into the map. So this is what happened when the robot has moved from this space to this space. If it could have continuously scanned all the observation, and it could have made this map as of now. But what happens if you see that when the robot moves, if there is any error in the sensor, say for example, the robot has perceived the direction, and the map may go like this, it may go like this, the map may come like this. If there is any error in the sensor, so the map perceived will be wrong. So that is why the SLAM problem is given utmost importance in the navigation. So you could see why sensor error happens and why people need so many sensors. You can see that this is autonomous driverless vehicle. You need this many sensors, radars, cameras, ultrasound sensors, and all these sensor details has to be fused, and the sensors readings has to be taken, and a decision has to be made, and localization has to be identified. So multi-sensor fusion is also another important research area, how to predict the force based on this multi. So sensors are prone for errors. So though there are accuracy and accuracy levels and other things, how these errors are managed. So that is also another research area in this autonomous robot navigation. So what are the uncertainties in this simultaneous localization and mapping? So uncertainties means, if suppose you are having a wheel with wheel encoder sensor, and your wheel will be tracking how much movement you have moved from point A to point B. Say if a robot has moved from point A to point B, so you can get the sensors, wheel sensors, that is odometry sensor. We call it as odometry sensor. The odometry sensor could have say that I could have moved for 1 meter, and it would say that my current position is 1 meter ahead of the previous position. Say if it is time t, and at time t plus 1, it says it is 1 meter based on the odometry sensor. What happens if there is some slippery surface? The wheels could have moved, but the robot could not have moved. So what happens? The robot could not have moved 1 meter, but something a bit lesser than that, and that is the uncertainty in the motion here. So we cannot identify the wheel slips. So that is why this problem happens. So when the previous position, now when it moves from this position to the next position, so the entire things will go wrong. So you may go and duck into a wall, and something will happen, an undesirable event will happen. An uneven surface, ups and downs will change your angles. IMUs have to sense that and correct it. And wheel may rotate without ground surface without contact, similar to wheel surface slippery. So that all happens. And so this is based upon the motion controls. What about observations? So sensors reading are prone to errors. So that also happens. So you could have moved actually 1 meter, and you may observe an object there. But when you observe it, the observation distance may wrong. So that also poses an error. So delay in sensor reading. So the robot may be moving very fast. So if there is any delay in sensor reading, that also is a problem here. Delay due to calculation time. So when you use lot of sensors and identifying a pose in that, locating a robot with lot of sensor data, it takes some calculation, and that also poses a problem here. So this happens when relative robot speed is very high. So there are as we go for higher things, we look into probabilistic approaches. So probabilistic approaches, they don't say that the robot is exactly here. So instead, imagine that you have a robot here, and it is moving from one place to another. And once it has moved, because of the sensor error, say for example, so actually the robot moved from point 0 to point X. Now instead of saying that a robot is exactly in point X, so they say probabilistically that it may be from anywhere in this region. The probability of at point X will be high, that is maximum, and the probability of other spaces may be low. That is what this probabilistic approach says. Instead of considering it as deterministically at one point, they consider it as probabilistic. So this probability can be improved when it comes across a known location. Say for example, it knows that I am at this door, then this probability distribution will reduce. If there is, it has a too much uncertainty, this distribution will increase. Say for example, let's see why this slam is very hard. So imagine that a robot initially looks into two objects, one to the left and one to the right, and these two objects, you can see that though the robot is at a stationary position, the robot considers that the object is somewhere in this area. It does not consider it as a deterministic point here alone. It considers that it is somewhere here, not in exact one position, because there are errors in the sensors too. That is why it considers like this. So now the robot moves from one place to another. It comes here. Now see that the position of the robot itself is a probabilistic representation here. So here it is a deterministic representation. Once it has moved from here to here, now it becomes a probabilistic representation. So the robot perceives itself somewhere around this area, not exactly in one place. So now you see that it perceives other two objects, and now what happens? So even now the probabilistic area has increased because there are errors in its own location itself, and there are sensing errors to the object. So it has increased this probabilistic distribution. So how this is going to end? So only when the robot goes somewhere and comes back and perceives the same object, then this probabilistic things can reduce, and you can, but you cannot come to deterministic point, but you can perceive that it is somewhere there, and when you move close to an object, then you can use some camera sensors or something and you can pick the object. So that is how this SLAM works. So how this robot path is estimated? So I said this is a probabilistic distribution. So in probabilistic distribution, if you see, so x is nothing but its coordinates x, y, theta, all these things from time 0 to time t, and m is the map. So it will keep on updating its map, and z is the observations that it made, and u is the control given to the robot. So in and mathematically, probability of the position x in the map m given the observation made when control u is given. That is how this is read. So this is how this is the SLAM. If you identify this probability, then this is called as simultaneous localization mapping. So let's see the graphical model of this. So now let us say that we are at position x of t, xt, that is at time t. X means it may be x comma y comma theta. So that is the state of the system x at time t. Now what happens? Now we should know where we were at xt minus 1. So this is a continuous process. I am explaining how it will happen continuously. So what it will do is, it will check for the previous information about the state. So at time t minus 1, where the robot was. And what is the control information supplied now? So now we are giving some control. Say for example, move forward. U is always a control, move forward, something like that. Or turn around, or turn to left, or turn to right, whatever it is. At time t, what is the control information given? And what is the observation made when control information is given? So when some observation, so with the help of sensors, it will observe some objects or whatever it is. What is the observation made? So there may be several other sensors. And what is in map? So map is another input. So is the robot identify something from map similar to something in the environment? So that has to be ascertained. Now, what is the control given at time t minus 1? That is also important. And similarly, what is the observation made at time t minus 1? And what is in the map at time t minus 1? That is also important. Now, with this information, we will move on to the next state. That is t plus 1, time t plus 1. At time t plus 1, it will estimate its state position, and it will also know what control it will give. That will lead to the next state and so on. So what it has observed. So the observations, everything will be updated. This keeps running from time t, t plus 1 and t plus n. So that is how this graphical model is constructed. So here, this is the unknown data, and this is what is observed, and this is what again unknown, which will be updated at every step. Just a minute. And now let us look into full SLAM. So in full SLAM, you can see that it is the probability of state and the map given the observation and the control given. So full SLAM estimates and keeps the track of the entire path of the robot. And for example, it is a maze solving robot. So as in
Hello, sir. Okay, participants, please wait until our guest come to the connection. Participants, please wait. I think sir is having some network issue. He'll come back soon. Meanwhile, we will have our next upcoming webinar is on circuit obfuscation and analog mixed signal design approach tomorrow by 5 p.m. to 6 p.m. by Mr. Gokul Ravi. His MS in Electrical Engineering, State University of New York, University of Buffalo. This webinar is powered by Impressions of SECEC alumni. Please to participate, and I request all the participants to wait until our guest resumes. He's having some network issue. Please wait for a minute. He'll be back. I'd like to announce our upcoming webinar. It is on circuit obfuscation and analog mixed signal design approach by Mr. Gokul Ravi, MS in Electrical Engineering, State University of New York, University at Buffalo. Scheduled on July 12th from 5 p.m. to 6 p.m. by SECEC Alumni Impressions. I request all faculties and students to attend the webinar and get benefited. I'd like to announce our upcoming webinar. It is on circuit obfuscation and analog mixed signal design approach by Mr. Gokul Ravi. His MS in Electrical Engineering, State University of New York, University at Buffalo. Scheduled on July 12th, that is tomorrow, from 5 p.m. to 6 p.m. I request all faculties and students to attend the webinar and get benefited. The link for the registration for tomorrow's webinar is posted in the chat box. Please register.
Hello, could you hear me?
Yes, sir.
Hello.
Yes, sir.
Okay. Okay. So I think there is some problem with my system. It got shut down. And
Okay, sir.
okay, now let us. I think it's almost we have reached the end, and this
Okay.
will be the cycle. So we have saw that initial state representation, then comes the controls, then comes the observation that what the robot sees, and this has to be represented in the map. So once this map is represented, when the robot moves from one place to another, then it again perceives what it is, then keeps on updating the map. This goes in a cycle. Once this is completed, your map will be ready. Sometimes in a structured environment, the
Sir,
map
excuse
can
me,
be
sir. Sir,
Yes,
excuse
sir.
me, sir. Please share your screen, sir.
Just a minute, sir. It's not visible, sir.
No, sir.
Not yet shared, sir.
Okay. Okay.
Hello, sir.
Yes, sir.
Can
Yes,
you hear
sir.
me, ma'am?
Yes, sir.
Okay.
Is that okay, sir?
Yes.
Sir, I have shared the screen.
Yes, sir. Okay, sir. Thank you. Thank you very much.
Is this, sir, planning versus?
Yes. Now, the next thing is about path planning, and I think so there are two things. As I explained, there are online algorithms and offline algorithm. Path planning, you can see that when it goes for from the start to the goal, it may go from one point to another. It may go stuck in a convex surface, then it move back and go. Then it is moment algorithm. Whereas if it is uh, planning algorithm, you can avoid this that getting stuck into a surface virtual obstacle. It can be considered as a virtual obstacle, and you may not move into the such surface. So that is difference between planning algorithm and moment algorithm. Please move on to the planning next please. Planning algorithms are generally slower but use better results than moment algorithm, whereas moment algorithm will be it takes faster, but it gets stuck into interior surfaces. Next slide, please. And there are several algorithms for path planning, and I thought of to go into some A-star path planning, but I think there's a little bit time available. We will just skip on with one introduction to just a small introduction to A-star. Move on to the next slide, ma'am, please. So there are many distance measures generally used in this path planning algorithms. So you keep on clicking, madam, 3 times. Manhattan distance is the distance that is taken like straight distance, Euclidean distance from point A to point B, and diagonal distance, it will move only in diagonals or in straight lines. So that is how the distance measure is taken. Next slide. And now the type of movement, as I said, there are straight line movements and diagonal movements. In straight line movement, the robot will move from point A to point B. Say next, click next one. Point A to point B. In diagonal movement, it will move from the center of one grid to the another grid. This is a grid map representation. And whereas in diagonal movement, if suppose the obstacles are obstructing the surface, and if the robot tries to move in between obstacles, actually the place of the robot, it can move from one place to another, but it will get obstructed by the obstacle. So it has to be inflated by the virtual obstacle. Next, please. So it cannot move. Next. So now, if suppose there is an obstacle, actual obstacle is there. Now we are going to inflate this obstacle. So hence inflated, so the robot can move from one place to another without the hitting the actual obstacle. Next, please. So the robot moves without hitting the next. So A-star algorithm, it is next slide. A-star algorithm contains it's a simple algorithm. Those who want to do path planning for a robot, then we can use this algorithm. It's very simple to understand. Also, it uses a function called it's a cost function f of n. It's the cost function f of n may be the distance here. We call it as cost, and g of n plus h of n. G of n is nothing but the exact distance from the starting node to the current node, and h of n is the estimated cost estimated cost from the goal state where we want to reach. Path planning has to be done from one point to another. So from that point to the current state. Next slide, please. So let us take this environment. We want to move from point A to point B. So we have to guide our robot from point A to point B. So we can see that it contains 3 boxes. The blue box now we have projected contains 3 boxes, one at the top left corner, one at the top right corner, and a lower box. The 14 is the distance from point A to point B, and 28 is the distance from point B to this box. Say for example, Y14. Now, what is the center distance from one box to another? Center to center distance in a straight line distance means it is a unit distance, 1 unit. whatever be the size of the box, it will take 1 unit. Suppose if it is box size is 1 meter by 1 meter, then from center of point A to next immediate box, center of point B will be 1. So I multiplied it by 10, so I represent it as 10. And if it is a diagonal distance, it will be root 2 units. Root 2 is 1.14, 1.414. That is, if you multiply it by 10, you can approximate it to 14. So a diagonal distance will cost 14 units, and a straight line distance will cost 28 units. So what happens is, so suppose now how it is calculated from point A to the current location, it is only one diagonal distance, so 14. From point B to current location, it is two diagonal distance, so 14 plus 14 is 28. So adding this two will give the total, that is 40, total cost of the current cell. So now you can click for 6 times, madam. 6 times you can just move it. Yes. So now what the algorithm will do is it will try to evaluate all the cells around the grid, that is around the grid. Now you can see that the box above the location A contains S as A, that is distance from the starting location as 10. Distance because it is straight line distance, and the distance from B, that is 38. That is two diagonal distance and one straight line distance. 14 plus 14 plus 28. So that is the 38. So that is how all the cells will be evaluated around it. And among that, it will choose a minimum cost cell. The minimum cost cell is 42. Next, please. 42, that is selected. So based on that, the next around cells are reproduced, and again next 42, that is next minimum is selected, and again now it has founded out the point B. Now from there it will trace back to the cell A. So you can see that all the cells are having minimum distance. So other than that, other cells will have maximum distance. So this is how the path is being planned. So the can more next case we have some obstacles. We will not evaluate that cells. All other procedures remains the same. Please move on to the next. Keep on clicking, madam. We'll go to the next slide. You go move on to the next slide. So now we'll see about the navigation. So once we have done SLAM problem, after mapping, we did path planning. Now we have obtained the plan for the path, how to navigate in the path. So there are several navigation problems. Navigation is nothing but the control. Once the path is obtained, you have to move the robot with a program to in a controlled fashion. That's it. There are several navigation systems: map-based navigation, behavior-based navigation, learning-based navigation, and communication-based navigation. So all these things. So I'll just discuss about this end of the slide. So all these things are sometimes when you have the map, and you need to have behavior also in combination with behavior means what it senses and how it behaves, what decision it takes, and learning means what it learns from that. Suppose it saw something and it goes and makes a mistake, it will learn from that. They'll use learning algorithms from that. Mostly you can see that, but every learning will be happening only in labs. So when a robot is made autonomous learning system, you could have heard about many machine learning algorithms and other things. Before it comes to practice, they have to do it a lot of time learning in the lab. So what actually the environment, what actually happens in the environment, everything has to be taught, and then only it will learn. So such learning based navigation is also possible. And when they go for multi-robot systems, they used to have communication-based navigation. One robot will communicate to another, and they will do some coordinated tasks. All these things are possible, and these are the future research areas.
So nowadays you can find only very few multi-robot systems in very few structured environment factories. Whereas when multi-robot systems come into effect with unstructured environment, there are a lot of research yet to be done in this area. And if you are interested, you can join this community of doing research in robotics. So I think we have come to end of the session. I thank the authorities of Savita Engineering College for giving me an opportunity to share my knowledge. So let us not limit ourselves to this discussion. This is very limited time. We cannot discuss much. But if you are interested, and you can contact me, the details are available in the website, and you are always welcome. So thank you. And if you have any questions, then we can go ahead.
Thank you, sir. Thank you so much. And that was really a wonderful session. And we convey our heartfelt thanks to you for sharing your valuable knowledge with us. So now we shall move on to question answer session. And we have
Yes.
few questions from the participants. So let me
Yes,
see in
ma'am.
the chat box. Okay. What is the best software to create a 3D environmental model workspace for mobile robot simulations? That was the question, first question.
3D environment model. My knowledge is limited to 3D environmental model, so I have not done much on three-dimensional spaces. I have done only 2D. But actually, there are a lot of softwares, open source. Open source is very limited, but I think 3D softwares, Open Modelica. So you can find Open Modelica is one open source software which you can use for 3D modeling, and but very difficult. MATLAB software is very difficult for mapping and other things. You have to write codes in it. So that is one thing. So you can try Open Modelica.
Okay, sir. Okay. The next question, a participant is having a doubt like, is it artificial intelligence plus humanoid robots and the autonomous learning machine will make autonomous humanoid robots? Is that so, sir?
What is it, madam? Can you repeat it?
Is it the combination of artificial intelligence, humanoid robots, and autonomous learning machine will make autonomous humanoid robots? Is that the
Actually, autonomous humanoid robots. So if a robot can do something without the human intervention, then it is called as autonomous robot. Whether it is a humanoid robot or whether it is a mobile robot, whether it is a drone, whatever it is. So if there is a minimum humanoid interaction, then we can call it as an autonomous robot. So it requires all these things. These robots required machine learning. These robots requires artificial intelligence is required. So without that, so all this combination put together, we call it as an autonomous humanoid robot. So we
okay,
can,
sir?
if it is an autonomous, it should have sensing capabilities, navigation capability, everything in autonomous. So it has to do it by itself. When only the human intervention will be there for just allocating a task. So whatever the task has to be given, only that thing will be given. So that is how autonomous robot is perceived. But still, there are a lot of research has to be done. So many a times, so these are taken interchangeably. So there are robots which are working with human beings cooperatively. So that is also called autonomous robots. So they will take inputs from human. They'll help human in doing some task. That's also called autonomous robots. So this is wide area, and this capabilities has to be put together.
Okay, sir. Okay, thank you. And the next question is from a student. What are the
Yeah.
subjects or topics to enhance my knowledge in artificial intelligence?
So this is very wide topic. So there are a lot of uh, courses that is being offered online in artificial intelligence. So artificial intelligence is a broad topic. So all this machine learning, deep learning, all these things comes under data science, all these things comes under this artificial intelligence. So you can find a lot of books are also available. So you can start simple, and you can go in depth. So if you could combine this with some task, if you try to do some project, that will be very easy for you to understand this artificial intelligence. Instead of you start with some basic knowledge, you try to do some project on it, then you'll try to understand what this artificial intelligence is all about. So people think that machine learning means machine learning or whatever else, artificial intelligence means the machine will start programming it by itself. But making such things is very difficult. That it needs a lot of learning before we put that into practice. So that has to be understand first. So only then we can do such things. So you have to start with small things, then you can build up things slowly.
Okay, sir. Thank you. The next question from the participant is, sir, is there any robot simulator that works with MATLAB?
There is a simulator called sim mechanics. That RoboSim. One simulator is called RoboSim. I don't know what kind of application he is asking for. So application, based on the application, the simulator has to be chosen. If the application is link based, so if they want to do some mechanisms or something, then it is different. And if they want to do some mobile robot application, then there are different applications they can try. There is a software called, there was one question previously, 3D simulator. They can try a software called VREP from Copilia Robotics, that is also available. So they can simulate it in 3D also. Even uh, this VREP software consists of lot of uh, predetermined robot models in it. So they can use that and try to experiment with those robots. So VREP can accommodate different programming languages: Python, C, C++, Lua. All these type of softwares can be coded. All this type of coding can be used in that VREP software. So in MATLAB, you can go for RoboSim, something like that, simulation.
Okay, sir. The last question from the participant. To communicate from one robot to another,
Yes, ma'am.
what kind of network can be used?
This is very broad question. So that depends upon what type of communication. It depends upon the distance at which you have to communicate. There are several communication methods. So there are Zigbee communication, wireless communication, Wi-Fi. You can, if suppose if you have to use it for very long distance, and even you can go for mobile communication. So it depends upon, again, I try to insist on the type of application you want. There are a lot of methods available, and the cost is also, the cost implication also will be there for which you are choosing. And the communication is, it's not, we cannot say that suppose if you are working between a small room and you have to communicate, then you can go for Wi-Fi or Zigbee type of communication. If you want to go for large communication, the communication range has to be checked. Accordingly, you have to put in the your devices.
Okay, sir. That was great.
Hello?
Thank you, sir. Thank you for this
Yes, ma'am.
wonderful session, sir. And
Yes,
I
ma'am.
hope you have answered all the questions, most of the questions from the participants. And we thank all the participants for joining us today. Hope you'd have enjoyed the session well. And most of the questions have been answered by the speaker. And would you like to say something for our participants, sir?
Yes, ma'am. Sorry, my computer got switched off in between, and I could not make the presentation with fullest satisfaction. But still, I hope that I will be available for the participants to contact me anytime. So all my contact details and everything is available in Analyst website, Department of Industrial Engineering. You can find my profile. So you can contact me for any things. I may be glad to help you in things that you want to know very well. So I thank everyone for your patient listening and the opportunity given by Savita Engineering College for sharing my knowledge. Thank you.
Thank you so much, sir.
Thank you,
We
madam.
would like to thank Ms. V. Gomati, Assistant Professor, EC Department, for coordinating this webinar. Thank you, madam. And I would like to announce about our upcoming webinar. Our upcoming webinar is on circuit obfuscation and analog mixed signal design approach by Mr. Gokul Ravi, MS in Electrical Engineering, State University of New York, University at Buffalo. Scheduled on July 12th from 5 p.m. to 6 p.m. by ACCEC Alumni Impressions. I request all faculties and students to attend the webinar and get benefited. Meet you all in the next session of our webinar series. And I kindly request the participants to fill the feedback link with correct mail ID. Link for the feedback form will be posted in the chat box and in our live YouTube streaming page. Please fill the form within 10 minutes after the session and receive your e-certificates through mail. Participants, kindly complete filling feedback form within 10 minutes after the session gets over. We like to inform that feedback link will not be shared through WhatsApp or mail. Thank you all for your participation and stay safe. The feedback form has been posted in the chat box. Participants, please fill the feedback form with the correct mail ID. I'd like to announce our upcoming webinar. Our upcoming webinar is on